Chapter 7, Dark Magic. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of several galaxies and discovered that stars in the outer region moved at nearly the same speed as those closer to the center. The Newtonian equation for orbital velocity is V of r equal the square root of g times m of r divided by r. The claim is that stars within spiral galaxies should orbit at a speed that is inversely proportional to their distance from the center of the galaxy. According to the Newtonian equation, the velocity should peak near the center and decline towards the edge. Assuming that the Newtonian equation can fully describe all galaxies is an oversimplification. The equation itself is limited even under its own original assumptions, since it relies on the orbit of a single test particle at distance r. Once additional particles are considered, the dynamics become more complex and difficult to compute, especially given that galaxies come in a wide variety of shapes and sizes. On top of that, Newtonian gravity was superseded over a century ago, so while it can still be useful in certain contexts, it's not the most appropriate framework for understanding galaxies. So why was this equation ever used? Well, it's simple, intuitive, and is expected to provide a decent first-order approximation. So why does it fail? Because galaxies don't reside within a vacuum. They are embedded within a sea of other galaxies. Another reason dark matter is so disappointing is that observations don't even suggest the curves are flat. There is a considerable number of galaxies with rising rotational curves. These sources indicate that rising velocities are incredibly common, yet virtually all generic sources, such as textbooks, college courses, and celebrity physicists, insist the curves are flat. Modified Newtonian dynamics is a popular alternative to the dark matter interpretation. The idea is that Newtonian gravity can be modified to include a critical value A, or acceleration, that serves as a relative floor to gravitational acceleration. Go.
All right, here we go then. So the quote is, either cosmology has a causative effect on inertia because it affects the state of the vacuum, which in turn affects inertia, or cosmology and inertia are both affected by the vacuum dynamics, which then enters cosmology, say at the cosmological constant lambda, and Mond through a zero that's approximately c times lambda to the 1/2. And there you have it.
In this quote, Milgram is proposing a form of Mach's principle. It's the idea that the properties of larger scales determine the inertia of local objects. As far as I can tell, Mond does not explicitly state this, nor is it derived from any theoretical foundation. With that said, it is evident that Mond is attempting to correct the inaccurate Spaceball's view of celestial objects. And presumably, the Mond constant comes from the distribution of matter and energy as a global parameter. Rising curves without dark magic. Our density profile, rho of r equals 3k divided by 2r, produces a uniform gravitational acceleration, with mass function m of r equals 2 pi kr squared. The gravitational acceleration becomes a equals g times m of r divided by r squared, which is around 3.49 times 10 to the negative 10 meters per second squared. This constant acceleration is similar to Mond's critical acceleration scale of 1.2 times 10 to the negative 10 meters per second squared, which was proposed to explain galactic rotation curves without dark matter. For circular orbits in this acceleration field, v equals the square root of 2 pi gkr. This predicts a rising rotational curve with v proportional to the square root of r. Deviating from the Keplerian, v is proportional to 1 over the square root of r decline expected in Newtonian dynamics with visible matter alone. At galactic scales of 1 to 30 KPC, our model predicts velocities ranging from approximately 100 to 570 kilometers a second. The common belief is that the bulk of galactic curves flatten at large radii. This is absolutely not the case. Large galaxies tend to have flat rotation curves, but the lion's share of galaxies are dwarf-sized with rising curves. Our proposed density distribution is not intended to be taken as a literal distribution for local scales. If used for a star, the equation is orders of magnitude too low. For a galaxy, however, the equation becomes much more accurate, with accuracy increasing with scale. Ideally, we would be able to use something more precise than homogeneity, but simple enough to provide the symmetry required for the Einstein field equations. Accelerating redshift without dark magic. The discovery of cosmic acceleration in 1998 was a watershed moment in modern cosmology. Type 1a supernova, used as standard candles to measure cosmic distances, appeared dimmer than expected, implying they were farther away than predicted by a decelerating expansion model. This result was interpreted as evidence that the universe's expansion is not slowing down due to gravity, but accelerating under the influence of a repulsive force. The term dark energy was coined to explain this unknown cause of acceleration. Historically, this finding should have raised serious doubts about the expansion paradigm. After all, the very reason the cosmological constant was introduced into Einstein's equations was to prevent gravitational collapse in a static universe. If the expansion is not just continuing but speeding up, it flips the problem on its head by trading collapse for runaway expansion. Yet instead of re-examining the core assumptions of the cosmological model, physicists simply added a new term to the equation and continued on. The accelerated expansion is now used to justify a growing dark energy budget, despite the fact that its nature remains entirely unknown. Dark energy is not derived from first principles. It is a placeholder, a fudge factor inserted to preserve a fragile and unstable framework. The observational anomaly should have triggered a paradigm shift, but it was instead absorbed into the existing model. Like dark matter before it, dark energy exemplifies the model bending to fit the data, rather than the data guiding us to a new model. Several attempts have been made to unify MOND and dark energy, but they all fall short of that goal. One example is TEVS, T-E-V-E-S. That's a relativistic MOND theory that adds scalar and vector fields compatible with lensing, but still needs a cosmological constant. There's mu essence, which is, it tweaks, it's just another version of TEVS. So if the scalar field plays the role of dark matter and dark energy. Then there's dark matter dipolar, which proposes a gravitationally polarizable medium that behaves like MOND on small scales and a cosmological constant on large scales. Gravitational polarization extension, that refines the dipole idea. Emergent gravity, and this suggests that there is an entropic force from dark energy. MOND-like behavior arises naturally from the de Sitter horizon. That's like a quantum gravity idea. A lot of these are, actually. Quantum gravity is the goal with a MOND, with a lot of the focus around MOND and dark energy. Yeah. Anyways, back to reading. Dark energy is unnecessary if the distribution of mass is the source of the redshift. The apparent acceleration observed in supernova data is typically attributed to a repulsive force acting at cosmic scales. But this is because the data is viewed through the lens of expansion. Gravity and gravitational redshift is inherently nonlinear, so redshift naturally increases more rapidly as light climbs out of deeper gravitational wells. On cosmological scales, the depth of the well is proportional to the distance the light travels. In standard cosmology, it's 1 plus z of r, or 1 plus z times r. In our geometry, it's 1 plus z times r equals 1 minus r divided by the horizon r. Here's another equation. You can just look through the equations. I'm going to stop reading the equations from now on. I think we've pretty well covered them all very well. This is the same curve that is interpreted in accelerated expansion in Lambda's DDM, except here it comes directly from the redshift profile. No cosmological constant is needed. There is no dark energy. The curve is just a natural result of gravity acting over long distances. Thomas Burchard has been screaming about the effects of cosmic inhomogenies for several years now. Burchard believes that these inhomogenies can be captured through an averaging framework and a concept known as back reaction. Burchard's view is that the total effect of the back reaction explains the acceleration and expansion of the universe without the need for dark energy. He argues that phenomena such as voids and clusters give rise to dynamic effects that are non-trivial. These inhomogenies give rise to differences in redshift, but they're not caused by expansion or dark magic. The observational diversity is a result of the differences in gravitational potential and the mainstream's unwillingness to comprehend the fundamental structure of the universe. The idea that expansion is a coordinate artifact rather than a physical process may be uncomfortable at first, but is entirely consistent with general covariance and the principle of relativity. There is no absolute frame of reference, no universal time, and no global energy conservation in curved spacetime. Once these lessons are internalized, the appeal of a static, gravitationally driven cosmology becomes not just plausible, but inevitable. The expansion paradigm has had a long run, but it's time to consider that the data may be telling us something else entirely.